Hello students, I am Farida and we are discussing today the topic expression for potential energy from our 8th chapter Electrostatics. In the previous lecture we studied about the potential energy and we got the expression for it. Now using those things we are going in detail with the uh, new topic, that is expression for the potential energy. So let us see now here. For this we required a diagram where we are considering the charge Q plus Q at position O. Now we are considering the another small charge Q0 at point A. This charge Q0 is at point or at distance R1 from the Q charge, source charge. There is a force of repulsion between them because both the charges are positive. The force of repulsion is shown by letter F and directed in this way. Now when we want to take this charge or move this charge from this point A to B against the electrostatic force F, then work is done. Okay, and this work done is stored in the form of potential energy, and so the potential energy of the system will increase. Now let us consider here. We are considering the charge. So let me write here. Okay, so let us consider here the Q charge, source charge. Let Q, positive Q, be the source charge, okay, and placed at O. Consider now a small charge, let Q0 be brought from point A to B from distance. Let us consider this distance is R1, from distance R1 to R2 respectively from O point. Okay, and it is against the electrostatic force, so we should mention here against the electrostatic force. Okay, so now whenever the charge is moved from one place to another place against the electrostatic force, then work is done. So work done, we will write here work done, and that work done is against electrostatic force. Against the electrostatic force F. In displacing the charge Q0 through small displacement dr. Now let us consider here this charge we are shifting from this position A to B, but let us consider small segments here on this distance. Okay, so through small segments it is covering this much distance from A to B. Now let us consider this small segment that is from position M to N. Now let us consider the charge is here somewhere and it is now displaced here. So how much distance it is covering? dr distance. Okay, so displacement becomes here dr. This is the vector quantity, so we place here vector arrow. So now because we are showing the distance opposite to the force, so it is displacing from this position to this position. Now in this way this charge will go through the small segment dr. From here to here this much distance is dr, suppose. Again here to here this is the dr. So from this to this position it is completing so many dr. Okay, so that time if you want to find the total displacement from A to B, that is integration of dr, isn't it? So let us consider here the work done, and that is when the charge is displacing from the small displacement, that is dr. So we can write whatever displacement is there, very small displacement we are considering, so the work done is small, and so we can say the work done is small, that is denoted by du, and that is equals to force. Which force we are taking? The opposite force we are taking here of the electrostatic, and into dr. So this displacement is against the force, electrostatic force. So in magnitude whenever you are writing, you are denoting minus F, okay, into dr, where minus sign shows the opposite nature of the force. So what negative sign show here? Negative sign indicates the displacement of charge Q0 is against the electrostatic force. So it is against the electrostatic force. So now this is the small displacement we are talking about. Okay, small displacement dr. If it is displacing from A to B, so how to write? Whatever change, that the change in potential energy, change in potential energy for displacement of charge from initial position A to final position B, that is given as delta U. Change in potential energy, it is called change in potential energy. And when the change in potential energy for displacement of charge from initial position A to final position B. So that is given as delta U is equals to I'll write here delta U, that is equals to integration of small du. So from where we shifted this, small du takes place when we shifted this from R1 to R2. Okay, integration from R1 to R2 we are doing, and we are displacing this charge from position R1 to R2. Okay, so integration is from R1 to R2, and that is equals to now here integration of R1 to R2, and what is the amount of du? That is minus F into dr, minus F into dr. Okay, so this is the equation number 1. Let us consider this equation as 1. Now we know the electrostatic force of attraction and repulsion, that is given by, what is the formula for electrostatic force of attraction or repulsion? If Q and Q0 are two charges, and these are suppose separated by some distance here R. So this is positive charge, and Q0 is also positive charge. They are suppose separated by some distance here, that is R. So how will write the force, electrostatic force? It is given as force, electrostatic force, that is equals to minus again, because we are taking force and charge in the opposite sense of the electrostatic force. So it is given now here 1 upon 4 pi epsilon 0 Q0 both the charges, product of two charges, and square of distance divided by square of distance between them. And whenever you are writing this thing, then you will put unit vector. And what is this unit vector? Unit vector is in the direction of the r displacement. Okay, so r cap is a vector in the direction of displacement. Are you getting? So we have this formula now. This is equation number 2, suppose. And negative sign indicates that R and F are in opposite direction. The displacement and the electrostatic force are in opposite sense. Now we will write the formula for a system. So for a system of 2-point charge, only 2 we are considering here, 2-point charge, for system of 2-point charge, what will be the work done or change of energy? We can say that is equals to du, and we know that is integration of r1 to r2 small du, and we have this value that is equals to integration r1 to r2, and this has, in the previous slide we have the equation that is small du is having this value minus f into dr. That same value we are writing here, and it is f into dr. Okay, now putting the value of f from equation 2 in above equation. See, what is the value of f here? That is minus 1 upon 4 pi epsilon 0 q0 upon r square into r cap. So this value we are putting here in this f's value, so we will get this equation. This is, let us consider this is equation 3. We are writing this equation 3 as delta u, that is equals to, now we'll write integration from r1 to r2. Let us consider this now, minus what is the value of this? 1 upon 4 pi so total value we are with a sign we are considering 4 pi epsilon 0 q into q0 upon r square. Let us write in separate form, because now I am considering the constant term together, and so I'll write it here like this, 1 upon 4 pi epsilon 0. So it is r cap into dr as it is here from this. Okay, this is the value of the force, and here we are writing dr as it is. So now from this we can write this as minus 4 1 upon 4 pi epsilon 0. This is the constant term we are taking out of the integration sign, and this q0 is also constant because charges are kept constant over there. Only the remaining thing which we are putting inside the integration sign, and that is 1 upon r square into dr. Okay, so unit vector is having the magnitude 1, that is also constant, that's why we have taken it outside. So now here integration of this is nothing but, again we will write here this thing minus 4 pi epsilon 0 q q0. Okay. And integration, now we will write this integration, we are solving this integration, and that is 1 upon r2 into dr, that is equals to 1 by r minus 1 by r. Okay, and we will put this upper and lower values, limits r1 to r2. This is called the upper limit, this is called the lower limit while solving the integration. So now here again I am taking this minus 1 upon 4, now q into q 0 we can write here now, and 4 pi epsilon 0, and this after solving we will get here. First of all we have to write here the upper value, so we are putting here 1 upon, what is the upper value, it is r2 minus, according to integration sign this minus is there, and minus of, again here we will write what is the lower value, that is r1 square sorry not square, so here I'll write, that is after simplifying we will get here minus q0 upon 4 pi epsilon 0, and here I'll write whatever positive thing, that we will take 1 upon minus get plus here, so r1, and this will become minus, so 1 upon r2. Okay, but again this is the minus sign over here, so after multiplying to this we will get here it will become positive now after multiplying with minus sign throughout. So here q0 upon 4 pi epsilon 0 in bracket we can write now, this will become positive and this will become negative, so r2 minus 1 upon r1, and this will be the final equation of delta U. So now here we can say, we can go ahead and we'll write here the final equation for du, and that is delta U, and that is nothing but integration of du from r1 to r2, and that is equals to, finally we got the equation, that is 1 upon 4 pi epsilon 0 q q0 into 1 upon r2 minus 1 upon r1. Okay, so the change in the potential energy depends only upon the endpoints and is independent of the actual part taken by the charge. Now suppose this is the charge here for consideration. I am taking here small, this is the q source charge I am taking, and the electric field is around it. Suppose this is the q0 charge. Now it is displacing like this, like this, like this, somewhere here, suppose, and it will come some at this point. So what is actual displacement? So this change in potential, whatever potential it has at this place, suppose A, at this place some VA potential it has, and at this point B it has some potential VB. So what is the change in potential? We never consider the distance covered by this charge from this or path of the charge. We only consider the shortest distance. So potential at this point, initial potential and final potential. So change in potential is final potential VB minus VA always. Okay, and so we can say clearly the change in the potential, change in potential depends upon the end point and not on actual path. This is important. Okay, so change in potential depends upon the endpoints and not on the actual path of the charge. So work done, whenever you are telling, so it is from A to B. Okay, so now work done, we will write work done, and that is denoted by W, and from A to B you are displacing the charge, so it will be AB, and that work done is nothing but the change in energy, change in potential energy. And so we have this equation that is equals to 1 upon 4 pi epsilon 0, this is the equation we are writing, and into q0 into 1 upon r2 minus 1 upon r1. So this work done from A to B is denoted by WAB, and WAB is equals to delta U, that is change in potential energy. Work done is change in potential energy. So it is equals to now 1 upon 4 pi epsilon 0 Q into Q0 into 1 upon R2 minus 1 upon R1. Now let us consider this Q charge, positive Q charge is there, and this Q0 charge is at infinite distance. Okay, this distance is infinite. So here R1 initial position we are telling about, so R1 is infinite, and we are bringing this charge from this infinite place to somewhere here at distance R. Okay, somewhere here at distance r we are taking, okay, from the origin O. So this is now r2, the final distance. So from A to B, if we are shifting this charge, so it is covering some distance here. And first of all, here we are taking the initial position of the q0, that is r is equals to infinite, r1 is equals to infinite. And here the final position r is equals to, let us consider here r, this much distance, let us consider r. So final distance r2 is equals to r, we will write. Okay, so what will be the potential formula for this? What will be the potential energy? So let us consider this potential energy, we will write here. Is equals to, I will write now, that is u. For this distance r, we will consider the total potential energy for the system we are considering now, and that is equals to, as we know the formula, 1 upon 4 pi epsilon 0, as it is we will write. And which charges we are taking here now? This charge q and q0. Okay, and what is the distance between them now? This is r, final position we are taking. Or if we consider this charge is q1 and this is q2, so we can write the formula here like u r, and that distance between them we are taking 1 upon 4 pi epsilon 0, and in general we can write now q1 q2 upon r. So this will be the equation for the potential energy, general equation we can say, and that is equals to 1 upon 4 pi epsilon 0 q1 q2 upon r. Okay, so this is equation number, I think, 5th it will be. This will be our 4th equation. So in this way we can give the expression for the electric potential. So it is very simple to understand. We are taking here, in short we will repeat it again to understand. So we have taken two charges here and they are separated by some distance r1, and now we are going to bring this charge from this position to this position. That time work is done, and that work done is stored in the form of potential energy. So here the potential energy is different, and here again the potential energy will increase or change. So whatever change in potential is there, that we are showing by the equation, that is du is equals to f into dr. Dr is the small distance covered while shifting. So the small displacement, first of all we consider from m to n, so small displacement occur over there. And so because this displacement is against the electrostatic force, we wrote here the minus sign. Minus sign indicates that the displacement is against the electrostatic force, and so we got the equation du is equals to minus f into dr. Now delta u is the potential change of potential energy through of the system when the charge is displacing from A to B. Okay, so this is nothing but the integration of all dr, isn't it? So we are writing here integration of small du, small change we are considering here, small change of potential energy. So how much displacement occurs when the integration is taken over here? So this much displacement is occur from A to B. So we are writing here what is the position of this A point, that is R1 from the origin. So we are initially initial limit we are writing R1, and where we are putting this charge at R2. So the limit is R2. So integration from R1 to R2, that is equals to minus f dr. This is the value we have written over there. Similarly now, if we'll see, then the force, electrostatic force of attraction or repulsion, that value is given, and this formula is for the force. With the help of Coulomb's law, we got this equation, and this equation we are writing over here as equation number 2. Now the total potential energy, change of potential energy we are writing, that is indicating by delta U, and it is integration of du, and that is equals to minus f dr, as we know this is the value of delta U. So here again we are writing the equation number 3. Now in equation number 3 we are putting the value from 2. So f we have from this equation. So putting this value here of f, will get this equation, and after simplifying it we will get the equation that is equals to this. Okay, so the change of potential energy is nothing but the work done. So work done is from point A to B only. So work done from A to B we have written, and delta U, that is equals to 1 upon 4 pi epsilon 0 q0, as it is the equation we kept here, that is equation number 4. And then we consider the general equation when, if the point is at infinite, suppose initially, and if it is coming to the position B, then what will be the equation, general equation that we have written? Suppose instead of q plus q and q0 we are taking these charges here, then after generalizing we will get this equation, that is potential energy, that is U at r distance. If the charges are placed, then 1 upon 4 pi epsilon 0 q1 q2 upon r. In this lecture we'll stop here, and in the next lecture we will discuss the next thing. Thank you very much.